Greetings, friends of astrobiology. Welcome to a brand new episode of Ask an Astrobiologist, a show where we celebrate science and celebrate scientists. My name is Sanjoy, and this program is made possible by contributions from the NASA Astrobiology program and the nonprofit Blue Marble Space. Today, we're very lucky to have a special guest in Dr. Steve Vance, who works at the hallowed ground of planetary exploration, the Jet Propulsion Laboratory in Pasadena, which is near the city of Los Angeles in California in the United States. Hi, Steve.
Hey, Sanjoy. Happy to be here.
I'm so looking forward to our conversation, but before we start, it's time for your monthly background quiz. Behind me is a fascinating location located on our beautiful planet, the Earth, and it is your job, you the audience, to guess where it is for our next episode. For prizes, you get, the third place winner gets the amazing NASA stickers. Here we go. The second place will get the stickers and the astrobiology graphic novels. And the winner will get the stickers, the graphic novel, and the SEGNE.org pint glass. Last month, we had a beautiful image that Mike can put up for a few seconds. Congratulations to those of you who got the right answer. It is the Bahamas blue holes. Those are many holes located in the Bahamas that get flooded, and they're really interesting because they get colonized by bacteria that do not depend on light to survive. That becomes important when thinking about life in extraterrestrial bodies, like we'll talk about today on this very show. So the third prize went to Evelina Dulguero. Congratulations, you get all the stickers. She connected from Garden City, Michigan. The second prize gets the stickers and the graphic novel. Chad Mitchell, congratulations, connecting from Spanaway in the state of Washington. And the winner of all three items is Omar Alaidi. Hi, Omar, and congratulations, who's connecting from Cairo, Egypt. Congratulations to all of you. So, what is behind me? We'll let you know next month on Ask an Astrobiologist. I can't say how I'm excited about this particular episode, Steve, because I'm personally a fan of the movie The Europa Report that I know you are a scientific advisor for. But before we get to that, though, like we like to do in this show, is turn back the wheels of time a little bit. And can you tell us how your interest in science first arose?
Yeah. Let's see. So going back to elementary school, I had books on planets. I remember distinctly an image of a fishbowl the size of the sun, showing how many Earths you could fit in it. And so I was intrigued by that. I was also a fan of the cartoon Muppet Babies, which I guess dates me a little bit. A show all about the imagination. And in the Star Wars episode, the Muppet Baby kids made a star field by poking holes in paper and black cardboard. So I was inspired to do that in third grade for my report about Uranus, and so I made a shoebox star field, and I actually had some accurate constellations on there, and a little glow-in-the-dark piece of plastic inside. So I guess I can thank the Voyager mission for first inspiring my interest in space.
Very cool. Yeah, I remember exactly where I was in 1989 when Voyager 2 passed Neptune. I was a very young boy, and it's still very vivid in my mind. So from our shoebox, you then did your undergraduate in physics at UC Santa Cruz?
That is correct. And like many undergraduates, I wasn't sure exactly what I was going to do. I was considering, going into the lucrative field of semiconductor development. But somehow that didn't excite me as much as the idea of trying to figure out what's out there, what is our place in the cosmos. And I guess like many people in our field, I was inspired in high school by Carl Sagan's Cosmos. So I had a VHS set of those, and I watched my way through them. So that came back to me, toward the end of undergrad when I was thinking about what I wanted to do and applying to grad schools. And I had an internship at an X-ray technology company near Santa Cruz. So designing lead enclosures for testing X-ray tubes, which was cool. But what was even cooler were sessions that I had with one of the employees there who had a master's degree in astrophysics. And he had in his head, the plan for humanity's exploration of the universe. And, the first couple chapters in those discussions were basically astrobiology. And this just happened to coincide with the discovery of ALH 84001, the now famous meteorite that still has ambiguous signs of possible life from Mars, which then kicked off the beginning of astrobiology as a field.
So following,
I ended up applying to grad school.
and that's where we met. You went to the University of Washington in Seattle, and your doctorate thesis was in geophysics. Tell us a little bit about what you did. I remember a big giant machine with a huge dial.
Yeah, well, I'll get to that. So I was admitted to the geophysics program, the department that later became Earth and Space Science, and I worked with an advisor named J. Michael Brown, one of the many Mike Browns of the world. He's a famous mineral physicist, so studies the interior of the Earth, and he was interested in applying some of his knowledge of thermodynamics and imparting some of that knowledge to me in a way that would allow us to think about how the properties of water and salty fluids change at the really high pressures that were expected to occur in the ocean of Europa. So Europa's a Europa moon of Jupiter. Its ocean had been just discovered at the time that I started grad school, and we had hints that there were oceans elsewhere as well. So there was a promising research direction in studying the chemistry of those fluids under high pressure. And so to do that, I built a device on wheels that allowed me to pressurize fluids to up to 8,000 atmospheres. And it had to be on wheels because it was an optical device. So I shined a laser light through the high pressure fluid, actually two laser lights, and created a sound pulse where the laser beams intersected. And I looked at how that sound pulse evolved by measuring the diffraction off of this diffraction grating that I had created. And so I measured sound speed with light, and sound speed then could be used to infer the density of the fluids. So that was the beginning of our research program. And yeah, the Frankenstein-looking device was pretty impressive.
So that was a device to measure the properties of water or salty water under really, really high pressures, more than the pressures we see in Earth's oceans for the application of Europa and also other icy moons. So perhaps let's take a step back now. And why icy moons? Why is the interest in these icy moons, also known as ocean worlds?
Yeah, well, okay, so at the beginning of astrobiology, the mantra was follow the water. We first wanted to just establish where there might be water because as is often said, everywhere on Earth where we find liquid water, we find life. So organisms are pretty good at making use of the resources that are available to them in almost every liquid water environment. And at the time that astrobiology started, we didn't know of any liquid water on present-day Mars. Mars continues to be a promising place to look for signs of past life, and perhaps now that there's some evidence for subsurface water, Mars will also be a place to look for extant life. So contrast that to Europa, where you have very likely up more than twice the amount of liquid water that is in all of Earth's oceans. In a moon the size of our moon, that makes Europa a pretty compelling place to go if we can get to this subsurface water, water that's under more than 3 kilometers of ice.
What's really exciting. What's really exciting about Europa, of course, is that the water is most likely sitting above seafloor, above rock. And we've had Alexis Templeton on Ask an Astrobiologist in the past, who is studying the process of serpentinization, which is a process of reacting volcanic rock, essentially seafloor rock, with ocean water that creates chemical energy for biology. Again, life that is independent of sunlight. Is that also an interest of yours?
It certainly is, and yeah, I can contrast Europa and Enceladus with the larger moons. Europa and Enceladus are in some ways Earth-like, in that at the seafloor of Europa you would have pressures that are comparable to the pressure of the Marianas Trench, and we think there's a good chance that the tidal activity on Europa, the tidal heating, can create hydrothermal systems, and I'm interested in the reduced materials that might be produced in those systems, that is, materials that are rich in hydrogen, which then provides the chemical energy for life. And so the next thing from follow the water is follow the energy. And so yeah, I like thinking of Europa as the Earth-like target for looking for life elsewhere in the solar system. I'd like to talk about Ganymede and Titan and the larger moons at some point. That's another set of challenges that I'm also interested in. But yeah, while I was building this giant Frankenstein apparatus that I wheeled around the hallways of our building in grad school, I was also doing some modeling. specifically considering how fractures might occur in rocks, in Europa in particular, but also in other worlds. So the idea is that in order to have water-rock interactions that generate this chemistry, you need the water to get into the rock. And so you need to know how fractures might form. And so I developed this model based on some work some people were doing in the context of seafloor systems on Earth to figure out how deep fluids could percolate. And the simple outcome of that work was to say, well, gee, the gravity is a lot lower, and so the gradient in pressure is a lot smaller, which means that you don't reach the pressure at which fractures close until a much greater depth. So in Europa, you might have fluid-rock interactions persisting to tens of kilometers, whereas 10 kilometers may be the upper limit on Earth.
Wow, very cool. So by modeling, you mean computer simulations, those are using the tools of mathematics and physics to predict how deep a fracture could go on Europa and where that water could travel to generate that chemical energy for life.
Yeah, since I can only go to Europa's seafloor in my imagination currently, I construct mathematical models that allow me to do that.
Very cool. So we think a lot about water in the solar system. We know of Europa, the moon of Jupiter, and Enceladus, the moon of Saturn. But there is water in more locations in our solar system. Can you give us a quick road trip across the solar system where you would find water?
Sure. So beyond Mars, there is water to be found, and amazingly we think that the planet Ceres, the largest body in the asteroid belt, is a watery object. It's spherical. It's twice the size of Enceladus, and it probably had a muddy liquid interior for a significant part of its history, if not into the present day. The main ocean worlds, places where we believe there are extensive amounts of liquid water, possibly more than on Earth, likely more than on Earth. The main ones are Europa, and then moving outward in Jupiter, Ganymede and Callisto, much larger moons, basically the size of the planet Mercury. And then at Saturn, in addition to Enceladus, which sits in the E-ring of Saturn, beyond that, farther from Saturn, is the moon Titan, which is also around the size of the planet Mercury. So in each of these, we have different lines of evidence for liquid water under the icy surface. And by under the icy surface, I mean hundreds of kilometers beneath the icy surface. So you have, basically Earth's upper mantle thickness of ice, and then hundreds of kilometers of ocean. So at low gravity, but high pressure. So it's weird to think of swimming around in this vast space of liquid water. And because we don't know how these bodies have evolved through time, we don't know their thermal evolution, we don't know what the composition of the oceans is. But we know in the case of Titan, Titan has this surface that's covered in liquid hydrocarbons. Some of those may make their way back in to the interior of Titan. We think the source of the methane that makes up a lot of Titan's atmosphere and the source of the nitrogen that makes up the majority of the atmosphere is from the interior. So we expect there's a lot of organics in that ocean. So it's interesting to think about whether those could serve as food for life in the ocean there.
What about further away? Maybe Pluto?
So going out beyond Saturn, Uranus and Neptune have moons that might have oceans in them. Promising moon of Neptune is Triton, which appears to be a captured comet. It's orbiting the wrong direction. It doesn't have the sense of angular momentum that all of the solar system has. It's going in the opposite direction. And so we think that it was captured. And that capture means a lot of tidal heating. And going even farther beyond that, the Kuiper Belt contains many dwarf planets, including Pluto. And because Pluto has its orbital interaction with its binary neighbor, Charon, it's possible that Pluto has an ocean. In fact, I guess the interpretation of the weird heart-shaped region on Pluto is that it's insulated by its nitrogen at the surface. And if you then model what is the temperature profile going into that highly insulating nitrogen layer, the water underneath can be in the liquid phase.
Wow, that's amazing to think that water, something we thought was like uniquely to Earth only a few decades ago, is probably all over the solar system. It's amazing. Yeah. Your T-shirt is making me very envious. I'm seeing Europa Clipper there, which is an exciting mission that NASA is currently putting together. I know you're involved with it. Could you tell us a little bit about the Europa Clipper mission?
Yeah, just a little bit about the Europa Clipper mission. The planned launch is in June 2022. Like Juno, that's currently orbiting Jupiter in an elliptical orbit to stay out of Jupiter's radiation environment, Europa Clipper will orbit Jupiter and fly by Europa a bunch of times. And so in order to stay out of the intense radiation environment at Europa's surface, we'll just zoom by, get a bunch of data, and then send it back to Earth over the ensuing 2 weeks or so, and then zoom by again. And by doing that, we can build up a map. And so this is our chance to go back to Europa with a suite of instruments much more powerful than what the Galileo spacecraft had, and to map the surface at resolutions down to less than a meter per pixel in some places, and to study the magnetic field around Europa to understand the ocean's composition from the field that's induced by Jupiter. And potentially, we'll be able to fly through plumes, if there are plumes at Europa, as there are in Enceladus, that is, emissions of water from the surface. We have evidence that there may be plumes, there may have been plumes actually when Galileo flew by there. And so we have very high-resolution mass spectrometers to sample those materials directly. Also, by studying the surface in great detail, we can understand Europa's geology and the overturning time. It's an important thing for me to note that one reason why Europa in particular is so exciting is that the high radiation, it sounds like a bummer for life, but it's actually a potential source of chemical energy for life, in that you can imagine the radiation breaking up water at the surface. Hydrogen is lighter and so preferentially escapes. So what you're left with is a lot of oxygen on the surface. And we've detected, Galileo saw signs of hydrogen peroxide, sulfuric acid, things that are very oxygen-rich, things that by themselves also don't sound so great for life. But we could imagine ways in which those oxygen-rich products break down into materials that could be useful for life. And so because the surface is very young, it's expected that those oxygen-rich materials make their way into the ocean. And it's possible even that the ocean is oxygen-rich in such a way that it could support a lot of microbes and possibly even larger forms of life.
That's fascinating, because you have at the ocean floor, you have this hydrogen being produced by this serpentization process, and these oxidants being produced at the surface, traveling down. And so life loves this thermodynamic disequilibrium of species. In fact, it's probably a universal properties of life. And so the fact that that could exist on Europa makes it a very compelling place to explore. For those of you who are watching, don't forget that you can ask questions live on the seginet.org chat, or if you're on Twitter, please use hashtag #AskAstrobio. I will ask those questions to Steve in a little bit. But first, I want to focus a little bit on two recent papers you published, one in the Journal of Geophysical Research Planets and one in Astrobiology, where you advocate for the use of a seismometer, so an instrument that measures the waves that propagate inside the planetary interiors, to say something about what it's made out of, that could complement existing instrumentation, or rather instrumentation that Clipper will have in orbit, such as ice-penetrating radar, which don't have as high of a resolution. Could you tell us more about these and how they can be useful in astrobiology?
Yeah, so one of the papers is in the journal Astrobiology, and it's meant to be an overview. So the questions you want to ask are, would seismology be useful in the first place in the way that it's useful on Earth? And so the question is, would any of these bodies, Europa, Enceladus, Titan, Ganymede, Callisto, generate seismic signatures on a timescale that you'd be able to pick them up? And could they be useful for determining what's underneath? So on Earth, we know about Earth's interior. We live on the soup skin of the very surface of the Earth. All of what we know of the Earth is just this very thin layer. And we know of what's underneath that because of seismic measurements. We know how big Earth's metallic core is, and we know basically what the mantle is made of, and that mantle convection occurs. And it's really important for me to mention that these hydrothermal systems that we're talking about on Earth are driven by Earth's internal heat. And the composition of those systems is determined by the interior activity of Earth. So existence on Earth is by permission of all these activities that are happening inside of Earth. And so understanding Earth's habitability is enabled by seismology. And so in a similar way, because everything that's of interest for life, where the life would be in these ocean worlds is in the interior, is in the ocean, we need a way to peer into the interior and understand what's happening. So getting back to the first question about seismology, the answer to whether there could be seismic sources seems to be a strong yes. The reason I feel confident about this is that the Apollo astronauts put seismometers on the moon. So there are still seismometers on the moon, albeit really low-resolution seismometers. But from the first instance those seismometers were put down, a continuous background of seismic noise was detected. So our moon is humming because of its flexing from tidal activity. So the strength of the tidal signals on the moon are correlated with the tidal cycle. And so if you think about the likely tidal energy on Europa, it's many factors more than it is on the moon. And so just on that basis, you would expect more seismic activity. And you can add to that the fact that Europa has a thin ice shell sitting on an ocean, so it's free to move, and the ice is more likely to fracture more easily than the rock. So we should expect that fracturing within the ice should be a source of seismic information. We could use that to figure out how thick the ice is. Also, what is the composition of the ice? So in many different ways, what is the working of the ice? In addition to that, there are suggestions that there might be fluids within the ice, and we have examples of this sort of behavior in Antarctica, in Greenland, where you have lakes that form at the surface of the ice due to heating from the sun. You wouldn't have that happening at Europa, but you could have other factors, materials within the ice causing the ice to melt. And you can use seismic signals to listen to the fluids flowing through the ice. We also think that as the ocean is churning underneath the ice, we might be able to hear internal waves breaking against the ice. And so we've modeled some of that in related papers to the ones that you described. We even have sounds of Europa that we've modeled using our computers. I'm excited from my foundational work as a grad student in whether we can use seismic signals to determine what is the composition of the ocean. So you can imagine that a magnesium sulfate-rich ocean would have a different seismic signature than a sodium chloride-rich ocean. And we're measuring those sound speed properties directly in the lab.
So it's like you're a doctor and putting like a stethoscope on the planet and listening to the planet's heartbeat to tell its health and what it's up to. That's so cool.
Yeah.
So,
and someday, you can imagine having a seismic network and being a doctor placing an ultrasound to listen for the baby kicking.
That's a great analogy. So ocean worlds are also interesting analogs to exoplanets, right? Planets that are orbiting far away from our sun. Could you tell us a little bit about the weirdnesses that ocean worlds have in our solar system and how to think about those as exoplanets?
Yeah, I think one of the most exciting parts of being an astrobiologist currently is thinking about the prospects for finding life in our solar system and where those places might be. And there are many different things that we're considering, like past life on Mars, life in ocean worlds. It's interesting to see this field developing over the time that you and I have been professionals, at the same time that exoplanets are coming into their own as a field. The term exoplanets is new, right? We called them extrasolar planets when we first started grad school, and that was a mouthful. So it's nice that things are getting a little more streamlined. But it's understandable that the search there is focused mainly on finding Earth 2.0, a planet like our own, and we have a good chance of doing that in our lifetimes. But I think there's good reason to think that there will be a far greater abundance of planets that are roughly Earth-size and are covered in water. Maybe they're farther away from their parent star and are more Ganymede-like or Europa-like. I think that super Ganymedes are actually a really important thing to consider, or super Titans, worlds that have a reducing atmosphere, but then an icy surface and ocean underneath. And an important thing there in thinking about Earth-sized planets that are covered in water is that for an Earth-sized planet, if you had tens, maybe 100 kilometers of ocean, the pressures at the bottom of the ocean would be so high that you create a different phase of ice, so-called high-pressure ices. There are many of them. The ones that I'm most concerned about are ice 3, 5, and 6. The Roman numerals applied to the ice phases really just note different crystallographic structure. So you can think of the familiar ice that we put in our drinks, that we skate on. It's called 1H. The H is for hexagonal, so it's a hexagonal structure of ice that has a certain configuration of the way the atoms make up the crystalline matrix. These other ice phases are more compact. So at high pressures, the molecules are condensed to form a more compressed state, because that is a lower energy state at those high pressures. And so being more compressed means that these ice phases are denser than liquid water, and so they sink. And so you can make these in the lab, and you can see them sink. And there's been some great work, some modeling work recently, looking at the rheological properties, that is, how these ices flow, how viscous they are at different temperature and pressure conditions, taking available information on that, and considering what solid state convection looks like, considering the role of melting in those ices. And you can think of these thick high-pressure ice layers in Ganymede, hundreds of kilometers of ice 6, as places that are active on pretty short geological timescales and move fluids around. And you can ask whether there might be a thin ocean underneath the high-pressure ice in addition to the ocean on top of the high-pressure ice. And so part of our work considering salts is pointing out that when you add salt, you make the liquids more dense, and liquids are more compressible. So you can actually create fluids you can create salty fluids that are denser than high-pressure ice. So you might have a dilute ocean on top of the high-pressure ice and a salty ocean underneath. So we're gathering those data very actively. I continue to work with the group up in Seattle, and we've got 2 really talented postdocs currently working with us, gathering these data so we can put those into models to think about under what conditions you might have layered oceans. And I like to say, you think of the less interesting in terms of habitability scenario in which you have ocean ice as a sandwich ocean. The layered ocean where you have multiple oceans is a Dagwood sandwich. So for those not familiar with old comics, Dagwood was a zany guy who liked to make really tall sandwiches. Just bread, meat, bread, meat, bread, meat.
So why is ocean ice less interesting for habitability?
Yeah. So talking at the beginning of this session about hydrothermal systems and water-rock interactions providing food for life. Well, you can't pump reductants into the ocean if you have ice preventing water-rock interactions from happening. It seems from this recent work on fluids flowing within the high-pressure ice that even if you don't have an ocean underneath the ice, water-rock interactions will create some amount of melt, and fluids will make their way through the ice regardless, because the fluids that are formed will be less dense than the ice. So maybe this is less of a problem than people first thought. But when we first discovered Europa's ocean and then discovered Ganymede's ocean around the same time, the discussion about habitability was, well, obviously Europa is much more interesting. We can't even think of life on Ganymede because the pressures are so high at the base. Of course, pressures high at the base also present problems for life. The high-pressure environment at the bottom of the Marianas Trench presents challenges for many organisms. They have to adapt to those high pressures to make sure their proteins don't denature. And so there's a set of obligate barophiles, organisms that are required to live at high pressure because that's where they've adapted to live. So we can imagine similar strategies perhaps being employed even in the high pressure environments at the bottom of Europa's ocean. But it's weird to think of organisms living in high pressure ice. And I think that there's a lot more experimental work that needs to be done to understand what kind of limitations high pressure ices and high pressure environments create for life.
So high pressure ice does not exist on Earth. So how do you create it in the lab?
You just squeeze really hard. So if you look at the Wikipedia for water, you can see a phase diagram for water, and you can see a region of pressure and temperature where water is a liquid, and then as you increase the pressure, you get to these high pressure phases. The reason you don't get high pressure phases on Earth is that they form at relatively low temperature, so they form at room temperature, but by the time you get into Earth's interior to pressures where you could have had high pressure ices, you've gotten way above room temperature. And so that's the only reason they don't form in nature. In fact, there have been suggestions that Ice 3 is formed in certain places in Earth's mantle where you have subducting slabs. And that, in fact, that was a Nature paper recently. It's not confirmed. It's an interesting finding. But yeah, it's easy enough to create those pressures in the lab and to make high pressure ices.
I just want to talk a little bit about that experiment, because you have to take two small diamonds and compress them, and it's that very small zone in between the diamond anvils that you can reach those really high pressures, which is an awesome experiment.
Yeah, so there are two ways that you do high pressure experiments. The Big Frankenstein thing that I built down the hall was actually a hydraulic experiment. And so I didn't have diamonds, I had sapphire windows. and I had a series of O-rings that created the pressure seal, and I pumped fluid into this fluid volume. And one advantage of doing that kind of experiment is you have a greater volume, so you're less subject to errors in measuring out the chemistry, and you're measuring the bulk properties of a bigger sample. Yes, to be sure, to make the higher pressure ices, or even ice 6, I was able to make an optical system. I reliably did that. But if you want to study conditions in Ganymede's deeper interior or occurring in exoganymedes, you need a diamond anvil cell, and so that's taking two DEM quality diamonds with very flat faces and making an anvil out of them. And you make this little casket with a space that's a couple hundred microns across. You make this very small volume of fluid, and then you just squeeze, you carefully screw the diamonds together so as they get closer together, they pressurize the fluid. And you can generate pressures. If you don't put fluids in, if you put solids in, this is the way to study rocks. You can reach 200 GPa, 20,000, 200,000 atmospheres. It's a lot of pressure.
Very high.
Yeah, very high. Still with my unit converter. But yeah, the pressures that we're concerned with are more in the 1 GPa to 5 GPa. So 10,000 atmospheres and above.
Very cool. Well, your job sounds absolutely awesome, Steve. We could talk forever, as we usually do, but I would like to open it up for questions from the audience. So again, if you're listening live and you're on Twitter, please use hashtag #AskAstrobio to ask us a question. And if you're on the SegaNet.org main chat room, type it directly in the chat window. So the first question is by Michael Wong, who asks via Twitter, so life emerged on Earth billions of years ago when our planet was a very different place. That's very true. Can you, Steve, please speculate on how Europa would have been different 4 billion years ago and how that would have influenced its habitability and its potential for an origin of life?
That is a great question. Thank you, Mike. So we think Earth was very reducing 4 billion years ago. So oxygen was a later invention. In fact, oxygen was a poison for the organisms that found themselves immersed in it as oxygen became more abundant on Earth. Similarly, it's expected that Europa formed as a reducing world, perhaps similar to how Enceladus is today. We have measurements of the plumes of Enceladus that suggest the pH of the ocean in Enceladus is between 9 and 11. So high pH means very basic fluids, and also was pretty basic when it formed as well. And to the extent that provided conditions for life to arrive on Earth, perhaps that was also perfectly fine for Europa. There's discussion and debate about how much oxygen-rich material is imported to Europa's ocean from the surface, and over time, whether that would have outweighed the reducing materials. And so if the field of Europa system science, where you consider the fluxes of different reductants and oxidants, you can construct scenarios where either Europa ended up oxygen-rich or stayed in its reduced state. I think either of those outcomes would be amenable to different kinds of life. It's just a question of what types of organisms you could imagine being in Europa. I think it's safe to presume that the origin of life, if it occurred on Europa, happened in a reducing environment. That then gets into questions about whether hydrothermal systems were the place that life could have emerged. There are some in the field of origin of life who suppose that continents, or at least solid liquid gas interfaces, were required, similar to what's behind Sanjoy. That's an interesting topic of debate, and I guess to the extent that's Europa becomes a place to test that hypothesis if we can confirm that there was an independent origin of life on Europa. Perhaps we don't rule out those hypotheses that continents are a good place for life to form, but we would provide support for a hydrothermal origin of life hypothesis.
Very cool. Thank you, Michael, for that question. Next one is by Andrew Smith, who asked via Twitter, when do you suspect we will find life on another planet?
So, okay, this is a wager, and it's a wager for me, between exoplanets and ocean worlds. So I'm more confident lately that Mars might have entered the running, if we believe the radar result that was published a couple weeks ago.
Indeed.
So I'm hopeful that in the next 20 years we could find life, and that's just speculating on the kinds of missions that might come to bear. There's a lot that can happen in 20 years, and having been involved with Europa Clipper for a while, I understand that planning missions is complicated. But being involved with Europa Clipper, I also have a lot of hope for the kinds of measurements we can make. First, in understanding the context of habitability better, and ultimately in searching for life.
Cool. Thank you for that. Next question, again via Twitter, is by Dina Kochi, who asks, how do seismic systems work on the surface of ice, such as on Europa, where there might be no connection to a rocky core? Because the waves don't travel through water, right?
Well, so waves travel through water. However, so the different types of waves basically are compressional, so like a slinky compressing. So those are called P waves. And then the other one is shear waves. So you can do this to a slinky or you can do it to a hose. That's always a fun thing to do. So the shear waves don't work in liquids. And so, if you want to study the interior of Europa or another ocean world, the ocean cuts out a lot of the information that you want. But the P waves that transmit through the ice into the ocean, into the rock, can then convert into shear waves, into combinations of shear and compressional waves. And so it's just a different type of seismology. The seismology generally works in the same way that it does on Earth. You just have to do a different type of predictive backtracking to understand what you're measuring. And certainly measuring in one place is difficult, but that's something that the InSight mission will be doing at Mars starting when it lands on November 26th. A little plug there. And I'll mention, as part of these papers that Sanjoy mentioned, we had a companion paper led by Simon Stahler, who's now at ETH in Zurich. It was a really great academic paper in terms of proposing naming conventions for the different types of seismic waves that would be unique to ocean worlds because of this ice-ocean solid interface that would occur. And I can point out furthermore, if we want to understand the existence of high-pressure ices and the layering and thickness of those ices, I think seismology is the only way we're going to do that. So I really look forward to developing that in the future as well.
That's cool. And this lack of transmission of P waves in liquids is how we discovered that Earth has a liquid core above the center core, of course, which is really cool. So seismology is a very efficient way to probe the deep interior of worlds. Following on the seismology question and on the Martian lake that was recently discovered, Marian Denton via Facebook Live asks, you mentioned using a seismometer to sense wave action below ice sheets. Would the newly announced lake at Mars' south pole be large enough to test that on? And also, has this been tested on Earth analog sites, for example, like Vostok in Antarctica?
So the answer to the Mars question is I don't know. And I also don't know if this has been studied in the context of Lake Vostok or other subglacial lakes. What's really interesting about ocean acoustics or seismology, this was recently demonstrated to me by a colleague here at JPL. You take a modern sensitive seismometer and put it on a tabletop at JPL, where I saw it demonstrated, or in Colorado, in the middle of the continent. One of the persistent signals that you see is the transmission of breaking waves on the coast, transmitting all the way across the continent. So you can see Earth's ocean seismically anywhere. And so our inspiration at Europa was to consider the analog of turbulent waves underneath the ice. So the assumption in that was in a paper by Mark Panning, is that the oceans are the characteristic ocean wave speed can be close to a meter per second, and that the ocean is turbulent and has a lot of energy in it. That's a discussion about fluid dynamics in Europa's ocean that hasn't been fully resolved. So it's fun that our work is touching on a lot of different active fields of research in Europa.
Yeah, absolutely. Your work touches on what the moon is made out of. It talks about, can contribute to the discussion on ocean convection, on habitability. the essence of an astrobiologist is oozing out in your work. It's fantastic. The next question coming from the SIGNet main chat from Richard Gordon asks, do all ices sinter?
That is a geology question. And although I got a degree in a geology department, I never did any sintering myself. But so sintering is sorting out by grain sizes, and to my understanding, or breaking off of crystals into smaller fragments. I don't know if that's been done with high pressure ices. There were some experiments in the 70s where a Canadian group claimed to have created ice 6 and then rapidly depressurized it at low temperature and had quenched ice 6. I suppose you could sinter that. I'm not sure what the application would be. And it's important to emphasize that high pressure ices, where they would occur in nature in these ocean worlds, would always be surrounded by liquids. And so liquids would become interspersed anywhere that any kind of fracturing would occur. I think your question is getting at something kind of profound that I don't really have an answer to. And so I'll have to think a little bit more about fracturing in high pressure ices.
Thank you, Richard. Next question is by Nitin, who asked via Twitter, how reliable is it working on microbes in serpentizing systems on Earth to that on exoplanets?
Okay, so the other bummer about Ganymede and Titan, at least from my simple modeling of water-rock interaction, is that if you expect fracturing to occur from cooling of the rock, and if pressure has a role in closing down any fractures that occur, Ganymede and Titan and Callisto have such high pressure that fractures close really efficiently. And from that standpoint, you wouldn't have a lot of water-rock interaction. Because I have a concern about this, and I want to believe that water-rock interactions can occur in these objects, I think about other ways that tectonics might occur, and that's something I've been discussing with a colleague, Paul Byrne, who studies tectonics, and so he comes at it from a different way. He also has sort of glum news about fracturing, but maybe there are other ways that rocks can sinter, and you can create more surface area for water-rock interaction. Because the fact that Titan has this methane-rich atmosphere suggests that water-rock interactions have occurred at some point. And the fact that Titan is a low-density object, it seems like there's currently not any way to explain the low density of Titan's interior without invoking hydrated rock. And so that, to me, suggests water-rock interactions occurred. So what that says is that my model is simple and needs to become less simple.
It's important to start with a model that's well constrained. And by model, again, we mean computer simulations. Tom Caruso asks via Facebook, the SOFAR channel, so the sound fixing and ranging channel, here on Earth acts like a horizontal pipe organ in our oceans, allowing sound waves to travel great distances. Do you think a SOFAR channel would exist in a deep ocean of ice-covered worlds?
Yeah, I like the acronym. It's great. The sound traveled so far. Yeah, and this is intriguing. Yeah, this inversion channel. Whales use it to communicate around the world. It's a really romantic idea. But my understanding is that SOFAR channel occurs because Earth's ocean is heated from above, and so my assumption is that the sound speed profile. So the sound speed profile for Earth does this thing where it decreases and then increases. And so the SOFAR channel is that inversion point. And so sound wave that starts in that inflection zone gets diffracted back into the SOFAR channel, whether it travels up or down. But if the sound speed is increasing uniformly in the ocean, which you would expect if the ocean is just if the temperature profile of the ocean is uniform, then there would not be a SOFAR channel. So
that's great explanation, Steve. Thank you. Jenna Kochi again asks, could you say something about international collaboration on astrobiology, particularly perhaps for the Europa Clipper mission?
I'm all in favor of international collaboration on astrobiology. So the Clipper in particular, we are just beginning to formally talk to the JUICE mission. This is the Jupiter Icy Satellite Explorer mission that's led by ESA. So they're going to orbit Ganymede starting around 2030. It's possible that Europa Clipper will be around at that time as well. Their goal is not just to explore Ganymede, though, but to fly by Europa a couple times, to fly by Callisto, and also to understand Jupiter and its environment. And so, in that sense, there's a great chance for ESA and NASA scientists to collaborate, to join their data together to make synergistic results. So in that sense, there's a great collaboration happening. Astrobiology is inherently collaborative. I've enjoyed, in my time working at JPL, particularly collaborating with the group ELSI in Tokyo. And so this is a group that's largely interested in Earth's interior and planetary interiors, and has really great expertise in that in particular, but also in hydrothermal systems. And so I think it's really important for scientists, but especially for astrobiologists, to visit and exchange information and perspectives so we can challenge each other and come up with new ideas.
That's a very romantic way of putting it. I would agree 100%. So on SaganNet, we often have early career individuals who are excited about astrobiology but not quite sure know how to get into the discipline. What kind of advice would you have for upcoming astrobiologists and how to get involved with science?
Well, so if you're a grad student, in that sense you're an upcoming astrobiologist, go to EPSICon. If you're an undergrad, go to EPSICon, which is the Astrobiology Science Conference, which happens every 2 years, and next year will be in Bellevue, Washington. So I look forward to revisiting old times with you, Sanjoy, at EPSICon next year. I hope that happens anyway. The other thing, so networking is important. That's what I'm saying. Short of going to a conference, you can seek out mentors. Professors don't get that many emails. They'd be happy to talk about their research, and they're actually pretty approachable. I would say a mistake that I made as an undergraduate was to be afraid of talking to professors because I thought they were this unobtainable level of knowledge. I'm the first in my family to get a PhD, so I didn't have a role model in that sense. So that's a big thing. And the other thing is, taking a lot of different classes, getting exposed to geology, biology, chemistry, the fundamentals, but also then learning about the disciplines that grow out of those, so oceanography, marine biology, that sort of thing.
I'm glad you mentioned the mentoring aspect. Could you tell us perhaps who are your mentors and how did they help you?
Well, I mentioned this colleague from the internship. So you can have informal mentors as well, people who inspire you. And I mentioned Carl Sagan, also informal mentor. I came to JPL, to be honest, because I was following Bob Pappalardo, who's the project scientist for the Clipper. I originally thought I would go to Boulder, where he was at the time, and then he got a job here. So in that sense, I wasn't even really strategically targeting a Europa mission. I just thought, here's someone that I want to work with, who seems to do good science and also seems to be a thinking and kind of everyone thinks, but I don't know. He's careful in a way that I relate to. I think finding mentors that you relate to is really important. I don't know. I'm a graduate model where you have a committee, and I was constantly checking in with my committee members. I was often changing committee members as I identified people who I wanted to learn from. So that's all really important. What else can I say about my personal mentor experiences? Well, I'll mention that as an undergraduate, I did an undergraduate thesis. So I built an experiment and I measured the stickiness of methanol frost to try to address how stuff came together in the early solar nebula on a length scale of greater than a centimeter, but less than meters, where gravity starts to become important. So anyway, my mentor there was Frank Bud Bridges, who was mainly interested in magnetoresistance and building new hard drives, but he had this side project with Doug Lynn on Saturn's ring, which we knew not much about at the time, and sticking of stuff in general. So I learned a lot of experimental stuff from him. He just said, here's the thing you should build, and then I went and built it. He, gave me advice along the way, and he also handed me a bunch of papers and said, read these. And so that was more of a kind of a soft mentorship of like, okay, go and learn some stuff. But he kept me motivated, and that was really important and I think pivotal in my development.
Very cool. Yeah, I will echo that advice of knocking on doors to people you admire is a good way to learn about how they got into the field and how they can help you get into it. So, great advice. We started this interview by talking about your participation as a science advisor in the movie Europa Report. Can you tell us more about how that was and working with Hollywood?
Hollywood. That was a unique experience. I've done various consulting things, various levels of formality. This one, and most of those have come about through my interaction with the Science and Entertainment Exchange, which is it's a AAA funded society that tries to connect scientists with filmmakers and writers and video game producers to help with public understanding of science. By contrast with the Europa Report, I just met a producer of the would-be film when I was volunteering at the JPL open house. They were looking for people to talk to because Europa was just coming into the consciousness of filmmakers at the time. There were actually apparently a couple of Europa movie concepts. But yeah, so for that, I ended up being connected directly with the writer for the screenplay. So at that point, they just had some money, and they had a guy who had a concept. And so I got to see a very early version of the script, and I got to talk to him mostly in the evenings after work, from my apartment, by the phone with this guy in New York, who I guess worked late. I suspect that my, going through what's cool about Europa and the fact that we were talking about the Science Definition Team report for the Europa Clipper, that we were going through many iterations of studying possible missions to Europa at that time. I suspect that led to the naming of the movie as Europa Report. And the theme of the movie is very talking about Europa and why it's cool. That was a neat experience. We had the chance later on. Kevin Ham was brought in also as a science advisor, and so the three of us got to go back and forth and talk about fun science things that could be put in that would make the movie feel more realistic. Artificial gravity, having a rotating spacecraft, the dangers of hydrazine, a lot of different stuff.
Very cool. Steve, you live a very exciting life. It's been a real privilege to talk to you today. We're right up time, so if you have more questions, please don't hesitate to reach out to Steve. You can find him on Twitter at Steve_Vance. Thanks again. I know you're an extremely busy scientist, and it's been clear from what you've been talking about that you have your fingers in a lot of different things. So thank you again for speaking with us. Please stay in touch with us here at Ask an Astrobiologist. For those of you who are watching, don't forget the background quiz. We'll give you the answer next week. And until then, stay curious. Bye, all.